Why, hello there, people. Welcome to Unit 5. This is Day 5. It covers 5.4 in the book. Don't be confused. I know this happens quite a bit, but this is Unit 5, Day 5 for our class. And we are going to talk about the first fundamental theorem of calculus. Why? Well, this is calculus class, and we should probably discuss things that are relevant, I don't know, maybe to calculus. And that's the first fundamental theorem of calculus. So let's proceed. Here's my favorite calculus textbook quote of all time. From Calculus by Ross L. Finney and George B. Thomas Jr., circa, or copyright, 1990. If you were being sent on a desert island and could take only one equation with you, this one might as well be your choice. I don't know why. That's confusing. I don't understand, but we have this anyways. Okay, this is the derivative with respect to x. That's what this part means. Of an integral of f of t. It just equals f of x. Okay, very simple. Nothing crazy, but very simple. All right. As with many of these things, all right, we will start to do these problems, and they will become, they will like cement themselves in your brain, kind of like was that an ear worm where you hear a song, and it just can't get out of your brain because that song is there all day. It's kind of like actually doing these things versus seeing these things. Now, one of the major things that should pop out to you here is I'm still using my main function here in this integrand, but instead of a t, my x is going in. All right, and that's really the big thing. But let's proceed and start doing some math. But before we do that, one thing I would like to point out, and this kind of draws on our prior knowledge here, is we know this is derivative. This is antiderivative, the integral. Okay, they sort of cancel each other out in kind of layman's terms here, meaning when we use opposite math to solve for a variable, if 3x equals 27, I am multiplying x times 3, right? The opposite of multiplication is division. So my x would equal 9. All right, so for this right here, you can kind of consider derivatives and integrals opposite maths. They cancel each other out. So I'm left with my function, except my x just goes into the original function. Okay, I mean, that's really all it is. But let's, again, let's start seeing some of these things in action. Now, this was not on your notes. This was just kind of like an introductory thing right here. And let's begin with the actual note-taking. The fundamental theorem of calculus, part 1. Part 1. If f is continuous on some interval from a to b, then the function capital F of x equals the integral from x to a of the function f with the variable t in it. Okay, so what does that mean? Anytime we see a capital F, they're just going to tell you that that's really the integration of your function f. When f is capital, that means integration in this notation. Wow, a lot of words that end in shun. Okay, now that capital F of x has a derivative at every point in that interval. And, badouge, the derivative, remember this is derivative. If I take this is the derivative of my capital F. That means I'm taking the derivative of my integral. And what do we just say happens? They cancel. So what happens here when I take the derivative of my integral, which is capital F, right there? Well, I take the derivative of my integral and they cancel. I'm just left with my original function and I plug an x in for it. There you go. Okay, that is basically what we just kind of had a precursor for. All right, nothing too complicated. It seems complicated because we have this lowercase f, this uppercase f. We have an integral. Why do we have to make it an uppercase f? Why can't we just say integral? Notation, my friends. Mathematicians are notoriously lazy for writing. We would rather do calculations out the yin-yang than write pages and pages, unless it's for educational purposes. And this is no different. Why would I want to write this whole thing right here when I can just write that? You know, lazy writers. Let's get to the meat and or potatoes of this theorem using common sense. Oh, thank God, Visca. Common sense, because I feel like calculus is not made of any sense, especially common sense. But you know, let's apply some common sense, okay? Let's find the derivative of capital F. So let's find the derivative of our integral here. All right? We're going to find the derivative of the integral of 3t squared dt. First of all, let's integrate, okay? Let's integrate 3t squared. Basic steps. I add 1 to my exponent. That becomes 3, right? And then I divide by that sum, 3. So I get t cubed, all right? That should be no shock. If I integrate 3t squared, I get t cubed, all right? So what we did was this step right here, okay? Let's associate this with colors. Let's integrate that. That's what we're doing in step 1. That's my answer, okay? Now, let's take the derivative of that. Let's take the derivative of the result from step 1. So now I'm going to take the derivative of what we got here, which was 3t squared, okay? So the derivative of t cubed, which was the integration of 3t squared. Okay, well, the exponent comes down. If I have t cubed, the exponent comes down, and I get 3t. I subtract 1, and I get squared. Huh, look at that. That's what I end up with. Okay, so when I take the derivative of an integration, I end up exactly with what I started with. How come? Because my derivative cancels the integration. All right? So what about this t and x thing? Just put the x in for t. Common sense. We know how to take derivatives. We know how to take integrals. If we were to do them both this whole process, we'd end up exactly with what we started with. Okay? Let me give you a visual. I mean, you might be like, Visca, I get it. I don't know. I just, the derivative of the integration of 3t squared dt. The derivative cancels the integration. That is blatantly obvious. And just throw your x in for your t. So, the first fundamental theorem. We take the derivative of the integral. That's what that means. And I hate how when I touch that box, that cursor pops right there. Little. It's almost like a little axis. Not only is it an X, but it has like arrowheads on the end. Do you notice that? Like, look at that. It's like I can graph something right on it. So it's telling me I'm not complete unless you put a parabola or something on me. It's weird. It's weird. Anyways, take the derivative of the integral. That's what this means. The derivative of the integral. Derivative of the integral. All right? The derivative matches the upper limit of integration. And that's why we need to switch these things. The respect of the derivative is to the x variable. That should absolutely match my upper limits or my upper bounds. All right? And here's a little tidbit that we did not discuss. My lower bound, my lower limit of integration is a constant. This a represents a constant. Whenever I have this situation here, it's easy. It's cake. All right? It is cake. It is chocolate lava cake, where the inside is this like warm chocolatey fluid and outside's a fluffy cake, and you bite into it and you say, who came up with this? And then you say, this is what I want on a desert island. Not a math equation, but lava cake, chocolate lava cake. You can tell I just like this stuff. Let's do some difficult math right now. Okay. Let's evaluate these things. I want to take the derivative of the integration here. Based on what I told you, I should end up with my main function again because these will cancel. And guess what? That's what I end up with. The only thing is my x goes in for t. There you go. Done. Happy? You should be. All right, let's take a look at the next one. Let's take the derivative of the integration. I should end up with my main function, shouldn't I? Except my x goes in for my t. I hope you're not confused because this is easy. All right, I won't say that a lot about calculus, but this is easy. Now, what obvious questions do you have? You should have questions that I know I would ask if I was a student. All right, and I am going to try to address those right now. Those questions should be the following. What if the upper limit is the constant and the lower limit is the variable? Like, see, the upper limit is supposed to be the variable. And the lower limit, let's call it 0, is supposed to be the constant. But what if that switches? What if this is my 0 and this is my x? Like, what happens? All right. What if the derivative variable and the upper limit do not match? Meaning, what if I have dt here, then I integrate this, and it's not a t, it's an x? You're like, what if they don't match? What happens? What if there is no constant for either limit? What if I take the integration and I have x squared and x? Like neither of them are constants. And by the way, Dr. Doofenshmirtz is probably my favorite all-time character from Disney that is kind of current from a cartoon. I love Dr. Doofenshmirtz. I will spare you the impersonation I do of him, but it is fantastic. Okay? So let's just move forward, shall we? You can see that was good. Anyways, let's do this. What if the upper limit is the constant and the lower limit is the variable? Take a look at what I have here. The integration with respect, the derivative with respect to x of the integration from 5 to x, not from x to 5. I'm going upper limit to lower limit of 3t sine of t. Remember, here's a little note. Negating the integral will flip the upper and lower limits. Let me say that one more time. Negating the integral, well, I should put that in parentheses first. Negating the integral will flip the upper and lower limits. That is one of our integral rules or antiderivative rules. I can flip the bounds and it negates the whole thing. So now I can go ahead and proceed. The derivative of my integration cancels, but I still have my negative. That's like -1. I can pull that out here if I really want to. Okay, the x goes in for t's, and everything else goes bye-bye. So it's the negation now. Well, let's do this. It's 3x sine of x, but it's the negative version. There you go. Now you know how to handle a problem if the variable is the lower limit and the constant is the upper limit. We know how to handle that now. Very, very good. What if the derivative variable and the upper limit do not match? Now let me go back because I gave you a very, very poor example right here. If they don't match, I didn't mean this was dt and dx. That was wrong of me to do that. Let's say this was x and this was, I don't know, x cubed. Okay, they obviously don't match. It's not x and x. That's what I meant when I said don't match. I didn't mean they were different variables altogether. My bad. My bad. So now let's go address that. All right. We can actually use the chain rule. Visca, what? Okay, just follow me. Follow me here for 1 minute, okay? We can use the chain rule. So what does that tell me? Well, I think I'm really going to do U sub instead of the chain rule. But I don't know. The chain rule I think is easier to do. Anyways. All right. Let's say U is x squared. That would make du 2x, right? Absolutely. So what do I do? What do I do? If this becomes my u for u sub, and the derivative and the integration cancel, that goes in for t, doesn't it? It's the cosine of u. Well, anytime I take the derivative of something, I got to multiply it times the derivative of the inside, don't I? That's where my chain rule comes into play. So what is u? X squared times 2x. And we should get used to putting that 2x out in the front. 2x cosine of x squared. So when you know the chain rule, do you really have to use u sub? No, you don't. I was just showing you a very, detailed example. I really just still plug my x squared, this variable, whatever it started with, okay? This variable, whatever it is, still goes in for t. But then I got to multiply times the derivative of whatever that variable is. Okay, whatever that expression is. So chain rule. This is really, you don't really have to do that, but that's kind of where it comes from. That's where I showed you. You can go from here right to here. So this is the upper limit, or upper bound, I like to call it. Then this is the derivative of the upper bound. Chain rule. Chain rule. What if there is no constant for either limit? Okay. I'm supposed to have a constant, Visca. A lot of these problems have zeros in the bottom. 0. Okay, we made a 5 here. All right. Does it matter what that is, if it's a 0 or 5? No, it doesn't, because my upper bound variable or upper limit variable still goes in for my integrand variables. Okay, so it doesn't matter if this is 5 or 0, whatever, as long as it's a constant, you're good to go. We don't have a constant here. So what are we going to do? We're going to split the integral into 2 parts. I should really have this dude holding up 2 fingers. Two parts. That would have been so much better. I've got to Photoshop that so he gets a second finger. Can I do that right now real quick? Let's see if I can do that right now real quick. Let's see how good my skills are. Ready? Let's go here. Let's blow this up a little bit. I'm going to do this. And I'm going to do the mode where it's freeform. So I'm going to try and get this guy's finger. Kind of like that. Then I want to do this. Copy it. Then I'm going to paste it right here. Then, for those of you guys that don't know about the software, I can set transparency. And I'm going to get rid of all this boom around here. So now I can kind of see behind it exactly. If I make that smaller and tilt that over here. Yeah, kind of. Oh, that's better. Is that two integral parts we switch this into? Group them together. Make that small again. Boom. Oh, beautiful. Look at me. 2. Yeah. I say there are 2. There are 2 parts. 2 fingers. Look at me. Seconds. When you know what you're doing with the computer, it's a beautiful thing. Except when you got to restart them because they crash and technology just sucks sometimes. But in this case, it doesn't. Look at me go. Fantastic. Anyways, back to math. What if there are no constants? We split the integral into 2 parts. Meaning, I take my upper bound to 0 and my lower bound to 0. Let me explain. I take the derivative of my integral from x squared to 0 of my original integrand, or my original function or expression. All right? And then All right, whoa, wait, am I rating this right here? Yeah, I take the difference of my lower bound to 0 as well, of the original function or integrand. All right? So remember, we can split these two things up. Okay, we can split two things up. Let me give you a little example of what I'm talking about here. This was another one of our rules back in the day. All right, if I have a graph, the integration really means area under the curve. Okay, so if I did something like and like let's say here's a point C, here's A, here's B. I can take the integration from B to A. It's the same thing as taking the integration from B to C and subtracting the integration from C to A. All right, I can take these two parts. Okay, ultimately, it works out perfectly. It's one of our rules, and that's exactly what we're doing right here. Okay, so bang, gone. Let's go back here. Oh, look at me. They found this guy safe. He was missing. Anyways. All right, so I'm going to integrate this first one. Again, derivatives of integrals cancel. I put my x squared in for my t. 1 over 2 plus e to the x squared times, that is not just an x. It does not match here. Chain rule. Times the derivative of x squared, which is 2x. I love this problem because it takes the previous question and ties it in with the current question. Minus. All right. Now, what I'd like to do here is one of the following. And I made a boo-boo. And when I say I made a boo-boo, I'm going to subtract those two bounds. All right? I'm going to subtract those two bounds because I want to flip that. Okay? And when I was doing this graph here, you may have had the question, and let's say this was A, and this was B, and this was C. And you might have said, well, Visca, when I take the integrand of this area from B to A, how come I'm not adding this area, all right, from A to C, all right, from A to C? Well, I kind of am because I subtract the two, but I'm going to end up flipping these. And what happens when I flip my bounds? Don't I negate my integral? I do. And what happens when I subtract a negation? I add. All right? So that's exactly why I'm going to do this. This, I would have added them, but I'm flipping them. You see what I'm saying? So that's why it becomes subtraction here. All right? Now, let's move forward. I put my 2x in to t. It is 1 over 2 plus e to the 2x. This is not just x. Chain rule. All right? That's just 2. And now I can just simplify this. And the only way I can simplify this is I just multiply these things together. They're over 1. So I've got 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. Let me get rid of this bad boy here. All right. So this is my final answer. That's it. So what do? I take these both to 0. Okay. I split these. Okay. Typically, I would say from x squared to 0. Then I would add the integration from 0 to 2x. But I want to flip these. Okay. So this problem in general is a great one. Number 1, it discusses not having a constant. Number 2, it brings the chain rule back in. And number 3, it also discusses flipping these. Okay, I would add these two areas together. but I want to flip the second one, okay? So I can have my constant on the bottom and my upper bounds or my upper limit can be my variable. The minute I flip these, I negate this, okay? The minute I flip those, I negate that. And that's what I end up with, okay? And I think that last explanation I just gave you was a million times better than any of the graphs I drew if they confuse. That's why I went over it a second time, okay? Because it might have been a little bit confusing initially. In fact, that's why I went over it a second time. Albert, he's so smart. I didn't know that's why I was holding up two fingers. He knew. He knew. All right. The second part of the fundamental theorem of calculus states, if f is continuous at every point in an interval, and if capital F is the antiderivative of f on that interval, okay? Capital F represents the integration, remember. All right? Then, whenever we integrate, and we know this already, okay? Whenever we integrate a definite integral, which means it has an upper limit and a lower limit, or upper bound and lower bound. Okay? I integrate this, and I put my b value in first, and I subtract the integration, putting in the a value. We know how to do this. Here's a brief example. If I'm going to do from 4 to 0 of 2x dx, this integration. Well, I integrate this, and I get x squared. I want that from 4 to 0, right? Don't I put the 4 in first, then subtract putting in the 0? And that should give me 16. That's all this is saying. This is notation. So why do I point this out? Because a lot of the time, on a test, quite frequently on the AP exam, they might give you one of these and this integration and expect you to find the other one. And without like having this pointed out to you, you might not make that connection. You should, but you might not. They might say, in that example we just did, the integration of 4 to 2, or excuse me, 0 to 2x dx. They might say, okay, you have this integration, and f of b equals actually 16. In fact, they might not even give you the details because you could do that out. They just might say this. The integration from b to a of f of x might be, I don't know, 7. And f of b is 16. What's f of a? And initially, without kind of like just breaking this down to the obvious, you might say, how the hell am I supposed to find this? Well, this is f of b minus f of a, isn't it? So this should equal 7. This whole thing is this. So if f of b is 16, I should subtract 9 to get 7. Okay? Or they might do something stupid, like they might say capital F of b minus the integration from b to a of f of x. Okay? And then you got to find f of a. But you have 3 pieces. These 2 should subtract to be this whole integration. Okay? And that's what I was trying to point out here. All right? And they ask every possible way you can imagine. They'll ask you about derivatives or integration. As long as you know the basics behind it, you should be able to do fairly successful in it. Okay? You should be able to do fairly well. All right? That is the conclusion of this lesson. We are done with Unit 5, Day 5. Adios, I bid you adieu, and I will see you later. Bye-bye. Oh, look at that. We were like less than a minute away from 30 minutes on the button. That is accuracy. And that was with me even putting the second finger on Einstein. God, I should clone someone. If I can clone a finger like that, I should clone another person. Can you imagine 2 of me doing these videos, talking back and forth? It would be nuts, insanity. Anyways, maybe that'll be for next lesson, cloning. See ya.